Okay, let's start. All right. If you have already checked the web page of Johns Hopkins University, you should have seen a continuous time convolution applet there too. In fact, you will find a lot of applets that may be beneficial for you throughout this course. Previously, I have shown you the discrete time convolution applet, if you remember. Now that we have also seen the graphical way of making continuous time convolution, let's try to see what sort of things can be done there. Unfortunately, once the web page is scaled for the projector, it's not okay. I mean, we do not see the right-hand side version somehow. We're not able to see the right side portion of the graphics, but let's try to see some convolution examples before proceeding with what we have been doing. So the graphical way of convolution, both in continuous time and in discrete time, is quite simple, as you see. All you need to do is you need to flip around one of the signals around 0, around the origin, and then start sliding that. The amount of slide will correspond to the output time instant. If the output time instant is, for example, 0, you just flip around one of them and don't do any sliding. And then you just take a look at the overlapping, because you need the multiplication. The multiplication or the overlap will correspond to a signal. It will be a continuous time signal. So what is the output at that time instant? You have to find the area under that multiplication signal. So you have to find the area under x of tau times h of t minus tau. H of t minus tau is the flipped around. At t is equal to 0, it means h of minus tau. So you multiply x of tau with h of minus tau, a multiplication, and you will find the area under the multiplication to find y of t at t is equal to 0. So how does it work? For example, let's try to draw something. And I strongly recommend that, just like in the discrete time case, I recommend that you draw something here. A lot of cases for visualization of convolution. As an example, let's draw one. Let me draw something narrower because I'm unable to go to the right hand side somehow. This is an error. But let's think of this rectangular shape as the impulse response. It could be the input signal too, because for convolution it is transparent. It doesn't matter whether this is h or this is x or this is h or and that is the other one is x. So we are just convolving now, for example, two rectangular shapes like this. You just drag here and you take a look at this. By the way, the left-hand sided signal is inverted, and at t is equal to 0, it corresponds to somewhere here. Now, as you proceed further towards right, they will start overlapping. Now, what is the overlap? The overlapping is drawn here, which is also a rectangular shape. For these two rectangular shapes, their multiplication will have a flat top. And that flat top reaches to its maximum here. In other words, the amount of overlap is maximum here. And then later on, the amount of overlap will be less, as you see. So it will be a narrower rectangular shape. And then there is no overlap after t is beyond some certain point. So what do we see? Just take a look at the shape at the bottom here. It's a triangle which is increasing to a maximum, which corresponds to the maximum overlap, and then decreasing back to 0. But of course, this output is for these two specific shapes. Let's try to draw some different shapes. For instance, what would you expect if I draw a rectangle here and a rectangle here? How will the convolution behave? Again, these are two shapes, two rectangular shapes, but one of the shapes is starting from the negative. So when I flip it around, it will be at its maximum already when t is equal to 0. So this would probably make a similar triangular shape, but the triangular shape peak will be at t is equal to 0, hopefully. So this is still t is something minus. This is where t is equal to 0, and look at the bottom figure over there. The triangle increased to its maximum, and afterwards it decreases again, as you see. So it's the same shape, it's the same triangular shape, but it is shifted towards left. Okay, now let me keep the right hand side of the figure, but at the left hand side I will try to draw. Well, even the negative portions are disabled here. I'm trying to draw something negative too, but apparently I cannot do that. So let me do something like this. Two rectangular shapes, and I'll try to convolve them with the right hand side. What do you expect? It's from the linearity of the convolution. The left hand side will contribute like a triangle if the widths are the same. If the widths are not the same, then it will be a trapezoid shape. And the right hand sided one will also produce some shape like that. And the result will be the summation of those, the combination of those. I don't know where this one came from. Probably from the previous input that I have tried. So I'll try to erase it and then do it again. Okay, well, something like this. Now, as you see, after flipping around, the right hand side, or the one at the left part, is flipped around towards the right hand side. So this comes here, and when I slide, that one will produce a triangle. Look at the triangle at the bottom. Now afterwards, the right hand sided one will produce another triangle, and the overall combination is those two triangles at the bottom. Of course, they may be negative or positive and things like that. That's always possible. Let's try to draw something like this, for example. How about a ramp shape like this, and another ramp shape similar like this. Now what will be the convolution? The convolution will just depend on the multiplication of these two after flipping around, of course. The blue one is flipped, and as you see, some amount of overlapping starts already, and it will increase. Is this the maximum? I don't know, because it depends on the values that are multiplying. So you have to take a look at the shape here. Will it have a larger area underneath than, for example, somewhere here? As you see, this time the values are larger, so there's a possibility that the area under this shape could be larger or smaller. You just have to evaluate. And after some time, there will be no overlap. Unfortunately, something negative is coming from here, which I didn't intend to draw, so I'll try to draw again, like this. Something like this is what I'm looking for. Okay. Look at the shape now at the bottom. It's just an arbitrary shape. Honestly speaking, if I ever intend to ask an exam question for you in the first midterm, for example, to draw the convolution output, it must either be something like a very trivial geometrical evaluation, like triangles, trapezoids, rectangles, and things like that, or it may be something that I just ask you to estimate, to roughly draw something. At some certain points, you have to give me the values. For example, what will be the value at this t is equal to 0 point? Label it accurately. So the questions may be like that. These applets, unfortunately, I wasn't able to draw negative things, so please try to draw negative things as well. Because when two negative signals are multiplied, it will produce something positive, for example. When a positive and negative side are multiplied, the result will be negative. Right? You have to be careful about the multiplication of the two overlapping functions quite accurately. So this applet is very beneficial. But it misses one quite important thing. It misses the multiplication with an impulse. So what would happen if you multiply with an impulse is something else. Let me close this and then I'll try to open the OneNote application again, the new page. So the thing that I'm trying to express is something like this. How would you convolve, for example, this? Suppose this is x of t, and there are two impulses here. The peak value is 2, and the values of these impulses are also 2 and 2, let's assume. This is up to capital T, this is at 2 capital T, and this is at 3 capital T on the time axis. So this is your input. And I want you to convolve this with an h of t, which is up to t over 3 with a magnitude of 1 on the time axis. How would you convolve these two? Again, if ever you have an impulse, but that applet is unable to insert an impulse inside. So you can only draw some finite values, not impulses. But convolution with an impulse is the easiest thing. Okay? It is just simply pushing this, the other convolved signal, to the position of the impulse and scale it by the magnitude of the impulse. The impulse magnitude is 2, so you have to scale this rectangle by 2 and draw it at 2t. So one component, let's call it y1 of t, would be like this. It would be from 2t to 2t plus t over 3, the same, exactly the same width, but the peak value will be now 2 instead of 1, because the impulse is scaling that. So this is one component, y1 of t. The other component is, let's call y2 of t. y2 of t will now shift the original input signal to the position of 3t. So it will be somewhere here. And the width will be the same, so 3t plus t over 3. And the magnitude is again 2 on the same time axis. So you have y1 of t and y2 of t. Clearly you need to have a y3 of t, which is the convolution of this rectangular shape with this rectangular shape. Now can you do that? These two are the simplest graphical shapes that we can think of, and in the exam you may be expected to clearly evaluate and clearly label. So what is the convolution of this rectangle and that rectangle? It starts from 0, because when you flip around h of t, for example, and start sliding, the overlapping starts at t is equal to 0. And then when t goes to the positive sides, it will start overlapping. The maximum overlap will be at t is equal to capital T over 3, the width of the narrower one. And over there, what will be the value, the peak value? It will be well, the shape will be rectangle with a peak value of 2. So what is the area under that? The area is 2 times t over 3. I argue that the shape is something like this. From 0 to t over 3, it will climb to a value. And that value here is 2t over 3. And for some certain amount of time, it will stay the same. Try to draw these things in the applet and try to see why this is the case. This trapezoid sort of thing is the same. And I also claim that this position is 2t over 3, and it declines back to 0 at t. All right. So this is the shape that I get from the convolution of the two rectangular shapes. What other things? So this is y3 of t. What other components do we have? I have y1 of t, y2 of t, and y3 of t. So we have to combine them, and the result you must draw is some shape like this plus this plus this sort of thing. And that will be y of t that you have to draw. And you have to, of course, clearly label the peak values, the time instances here, 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 and here. And you have to give me these values. What are these values too? Yes?
Hocam diğer uçtaki yandan çıktı listeyi niye görebileceğiz?
All right. The maximum overlap, let's flip this one around. I will try to draw it with a different red color. I don't know if it will be a red there. But when you flip this one around, okay, you will see this rectangular shape. Will you? Do you agree with that? Now let's push this rightwards to the right. Then it will come here, here, and then it will come here at some point, right? That point is when t is equal to capital T over 3. It will be exactly like the original black box at that position. Now multiply this red shape, this one, with the top figure here. What will be the multiplication? The multiplication will be, I'll try to draw here, the peak value will be 2 because this was 1, so 1 times 2 will be 2. A rectangle like this. Is that okay? So the value is 2 and it's from 0 to t over 3. So what is the area underneath? 2 times t over 3. If you go further to the right, if this thing further moves to the right, it will still be like that. After some time, when t becomes greater than 2t over 3, then the overlapping will be smaller and smaller and it will be declining back to 0. No? So that is the thing. That's the area under the multiplication signal. Those multiplication signals in many cases are either triangles or rectangles or simple shapes with areas that can be manageable, okay, in the exams, for the exams. But for general shapes, please run the applet and see what's going on. And I strongly recommend that you draw those two shapes and try to convolve and see that trapezoid shape. Yes? No, it will. No, it will be at t. Yes, because at let's see. You may be right. At 0, it's here, and at t over 3, it reaches to the maximum. At 2t over 3, it is still in the maximum. Yes. At t, it is still at the maximum. You're right about that. So it's not like this. Your friend is right. It goes up to t. And at the position t plus t over 3, it goes back to 0. Yeah, the overlapping vanishes only then. So that's right. And therefore, it must be something like this. Yeah. So this is the strategy that you must follow, and usually the students are not very comfortable with the impulse things. When impulses come into the picture, you just fail to implement the graphical convolution. You have to just stop the graphical convolution if there's an impulse. You have to just move the signal there. As an exercise, please do something like this. What if here you have a rectangle and at some other place you have another impulse? So impulse versus impulse convolutions. It's still the same. Impulse convolution with an impulse is an impulse. Where is it? You must just move the impulse, one of the impulses, according to the position of the other one. If this impulse is at, I don't know, for example, 2t, then the convolution of this 2t position with this 2t position will be at 4t. It will be an impulse, a new impulse, somewhere here at 4t, for example. And the convolution of this impulse at 2t and this impulse at 3t will be an impulse at 5t. Yeah. Okay? Please try to exercise with these things. And if you are ever confused about what the result would correspond to, please come and ask, or at least look for the result. If you never exercise with these things, then you will never be aware of the problems that may confuse you. Okay? You must be confused already before the exam. If you are confused during the exam, that's a mistake, right? Okay, so this is all about convolution. And please remember where this convolution business came from. It came from the concept of linear and time invariant systems. Linear and time invariant systems have impulse responses, H. So the methodology to find the system response, LTI system response, is by convolving the input with the impulse response. And it will give you the output. It all comes from linear and time invariant systems. So I will open a new page, and let's briefly remember what the convolution is and what the properties of linear and time invariant systems are. System properties. First, let's remember that if you have a linear and time invariant system, LTI system, the output Y will be the convolution of X and H. And that is defined to be over, let's say, K from minus infinity to infinity, X of K, H of n minus K. Or if you interchange the places of X and H, it will be H of K, X of n minus K, the same summation from minus infinity to infinity. And in continuous time, Y of t is X of t convolution with H of t, which is defined to be an integral from minus infinity to infinity, X of tau, H of t minus tau d tau. So the summation is translated into the integral. And what are the properties that we can say about linear and time invariant systems? Previously, if you remember, we have covered a lot of properties of systems in general, not necessarily linear and time invariant. In fact, linearity and time invariance were by themselves properties of systems. But once we have those two properties, linear and time invariant properties, then we do have some very nice shortcuts to check, for example, causality. Is the system causal or not? How do we check this? From normal systems, it requires that the output must appear after the input. For linear and time invariant systems, the causality condition is a little bit simpler. It must be something like this: h of n is equal to 0 for all n less than 0. Or h of t is equal to 0 for all t less than 0. It means that the impulse response should start from 0 and extend to the positive times. That's it. So if the impulse response is a rectangular box in the center, for example, starting from -3 going to +2, a box like that, is it causal now? No, it's not, because h of t is not always 0 for negative times. Since it's the impulse response, the response of the impulse must come after the impulse. Impulse is in the center at 0, so the impulse response must exhibit itself after t is equal to 0. So these are, for example, all causal impulse response linear and time invariant systems. But if you have something like this, this is not a causal LTI system because it's in the negative time, a non-zero. Okay? So causality check is as simple as that. Another simple thing is about stability. Previously, I had some ambiguity about describing what systems are stable, what systems are unstable. But now that we have linear and time invariant systems, we have impulse responses, and just by inspecting the impulse response, I'll be able to say that the system is bounded input, bounded output, stable or not, by this. In discrete time, this summation, absolute value, or the magnitude h of n, must be finite. So this summation must be finite, and in continuous time, the corresponding integral from -infinity to infinity, absolute value h of t dt must be finite. So if these conditions hold, we say that the system is bounded input, bounded output, stable. Simple. So let's take a look at these two shapes. One of them is causal, the other one is not causal. Are they? Do they look stable or not? They look stable because they are both finite energy sort of signals. In fact, if they are finite extents, if the impulse response starts at some point and then ends at another point, and in between all the values are finite, clearly the absolute sum of the area underneath is finite. It never blows to infinity. The infinity phenomenon happens in many cases if the impulse response is infinite extent, if it extends to infinity. Then you have to find an infinite integral or an infinite series sum if it is discrete time. You have to sum them up. Does it converge to a signal or a value? If it converges to a value, then you say it's stable. If it doesn't converge, then it's not stable. Let's see an example. H of n is equal to u of n. So the impulse response is a unit step function. That's a linear and time invariant system with an impulse response. What would you say about stability? First of all, what would you say about causality? Is it causal? Yes, it starts from 0 and goes to the right. Is it stable? What is the infinite summation of ones from 0 to infinity? Infinity, it's not finite. So it's not stable. This thing doesn't hold. How about this one? H of n is equal to minus 1 to the power n u of n. Is it stable? It's not stable either, because you have to take the absolute value in the summation. If you take the absolute value, all minus cases will become plus, and the stability of this new signal is the same as the stability of u of n only. Minus 1 absolute value will be 1. It's like all ones you are summing up to infinity. So this is also unstable. This one is also unstable. One over n u of n. No, u of n minus 1. Is it stable? It starts from 1, then plus 1 over 2, plus 1 over 3, plus 1 over 4. Is that a convergent sum? The answer is no, it's not. Beg your pardon? At n is equal, that's why I wrote u of n minus 1. It doesn't include n is equal to 0. It starts from 1. But the series summation is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, etc. And the summation diverges. It doesn't converge. This is unstable. How about this one? One over n squared, u of n minus 1. Again, starting from n is equal to 1. Does this converge? This one converges because the square denominator is a convergent series sum. This is stable. All right. Let me ask you a question like this. H of t this thing, which is t to the power t, a very fast growing thing, up to 1 million seconds. So the h of t that and it starts from 0. So the signal that I'm trying to write in closed form is, in open form, in fact, is t to the power t u of t minus u of t minus 1 million. This is h of t. It's a huge signal, in other words. So is it a stable system? Yes, it is. Because no matter how big it is finite. It stops at some point, and the area underneath is finite. It's a huge number. 1 million to the power 1 million is unacceptable, of course. It's huge. But it is finite. It is less than infinity. So I would say it's a stable system. How about this one? Example, h of t is equal to sine 2 pi t u of t. Do you agree with your friend? Is it unstable or stable? It is definitely unstable. Because the positive and negative, there are positive and negative oscillations in sign, but you have to take the magnitude, so it will always contribute positively, and as t goes to infinity, the area underneath will diverge to infinity. So this is unstable. It may be slowly increasing, but eventually as t goes to infinity, it will diverge. So these are the examples that I can think of. Of course, in the book by Oppenheim, you will see a lot of exercise questions. Please solve them and see whether your intuitions are correct or not. Now, just for the sake of completeness, I'll try to show you a proof of this absolute summation or absolute integration check for the stability. How come it gives you a bounded input and bounded output stability? The proof is as follows. For bounded input, bounded output signals, we have the magnitude of, I'll try in discrete time because it's easier to explain everything in discrete time. Instead of integrations, we start with the summations, but you can always extend it to continuous time. This thing is less than a bound for all n. So this is bounded input that I construct. Then y of n is the convolution of h and x for k from minus infinity to infinity. This is the input-output relation, the convolution. Now I'm going to put absolute values in both sides of the equation. Then from the triangular inequality, absolute value of a plus b is always less than or equal to absolute value of a plus absolute value of b. Is that okay? Because some of them could be negative. Their summation would be smaller. But it is upper bounded by absolute value of a plus absolute value of b. The same holds for the infinite summation too. What I mean is this. This thing is always less than or equal to the absolute value inside the summation. K from minus infinity to infinity. Absolute value hk, x, and minus k. This is the triangular inequality. And then this thing is equal to k from minus infinity to infinity, absolute value of h times absolute value of x. Okay? Now look at this. This is upper bounded by b, by definition. It's a bounded input. So this is always less than or equal to b. So I'm going to write it like this. The summation this time will be smaller than or equal to k from minus infinity to infinity h of k times b. And I want this thing to be less than infinity, finite. And how does it happen? This side of the equation holds for any finite value of b. It means that it's equivalent to saying summation k from minus infinity to infinity. The scale doesn't matter anymore. It doesn't change the infiniteness. H of k absolute summation must be less than finite. And this is exactly what we claimed, right? That's why for linear and time invariant systems, absolute summation of the impulse response must be less than infinity, must be finite. Corresponds to bounded input, bounded output stability. Now, seeing this kind of a proof, will you be able to prove the same for continuous time? Can you also illustrate that h of t absolute integral must be equal to or must be less than infinity, must be finite? I will also do that. Okay. To to make sure that you understand how to illustrate the proofs of these things. In continuous time, this time let's write y of t is equal to integral from minus infinity to infinity x of tau. Let me write h of tau because it's easier to write it that way. H of tau x of t minus tau d tau. And just like in the previous case, I'm going to put absolute values in both sides of the equation. And the triangular inequality now says that if you push the absolute value signs inside the integrals, it will be less than or equal to. Like this, h of tau, x of t minus tau, d tau. Like this. It's the same triangular inequality that I'm writing. Then I can split the absolute value signs into the two terms, h of tau, absolute value, times x of t minus tau, absolute value, d tau. Now x of t minus tau in absolute value is less than or equal to a bound b. So this means in order this thing to be finite, we need integral from minus infinity to infinity h of tau, absolute value, d tau, must be less than finite. Exactly the same thing that we did for the discrete time case. Okay. Now these two are the critical properties, the causality and specifically the stability, because stability is a required thing for control systems. We want to usually stabilize, or we want to obtain a stable control system in the next semester's course. And you just find or detect whether they are stable or causal just by looking at the impulse response, if it is an LTI system. So when I ask you some questions, I may give you a table, for example, with a lot of input-output relations, sort of system representations, and the columns will correspond to invertible, stable, causal, etc. Lots of system properties. You will put a check mark if it obeys, or put a cross if it doesn't obey, for example. And if you can detect that the system is linear and time invariant, the best way is to look at the impulse response for stability and causality. All right? So, let's give a 15 minutes break now, because in the next hour we will start a new representation of the systems, which is something else.